And I'd like to welcome to the stage Michael Dow from Dream Sports, who will be emceeing this portion of our program.
Okay. Hi, thank you for that wonderful introduction. I have the auspicious honor and incredibly vital role of introducing all the excellent speakers and research awards that we have lined up in the afternoon. The format is naturally very similar to what you saw in the morning with Alari presenting. And first up, we have Sunil Agarwal, who is a professor here at the Department of Mechanical Engineering and Regenerative Medicine, if I have that correct, which is a fascinating combination. So please welcome Sunil.
Screen mode.
You're good to go.
Well, first of all, thank you very much for inviting me to give this talk. My name is Sunil Agarwal. I'm a professor in engineering as well as rehabilitation medicine. I direct the Columbia Robotics and Rehabilitation Laboratory, which is partly here in the engineering campus and the medical campus. A lot of work which we do is to look at human movements in general, people who are impaired, somebody has a stroke, somebody has a spinal cord injury, cerebral palsy, and so forth. So we create robotics as a wearable devices, which we use to train the human movement or train the nervous system using robotics. And we do a number of experiments in our medical campus, recruiting people who have these neural impairments and show the efficacy of these ideas with technology. So what we are going to do today is to see how we can use these same neuroscience principles to train human movements in sports. So just to kind of give you a quick outline, I mean, we in our daily life, we do so many different functions, right? We walk, we stand, we talk, right? We don't even think about what we are doing, right? And we are able to do that. And if I look at behind the scene, it's the central nervous system, the peripheral nervous system, and the musculoskeletal system is sort of coordinating all of these movements, right? And but we know that the brain has the ability to learn, right? Whether we look at young babies who are sort of learning to walk, or old individuals who are sort of kind of looking at how to keep balance. And often they undergo this training through physical therapy, right? And the part of the motivation for physical therapy is that there is a whole scientific framework of neural plasticity, right? That the brain has the ability to learn and change through repeated exercise or practice. And the nervous system reorganizes itself kind of through these repetitions. And some of the motor training principles are we do many repetitions, we kind of progress the challenge over time, right? We make it specific, right? I mean, if I want to walk, right? I mean, then all the training is towards walking and then so forth. So what I'm going to do is show you the efficacy of an idea of something that we had published almost 15 years ago. What you see here is a person using a robotic exoskeleton, right? This is something that we designed in our laboratory. And the example that we'll take here is that human walking, right? I mean, we all walk every day, right? We have a certain pattern of walking. In fact, we can look at somebody from the back and say, well, I mean, it's that person walking, right? It's so ingrained in our brain. So the question we asked ourselves, and this is a neuroscience question, can we train somebody to walk in a different pattern, right? So here, what we are doing an experiment where we want individuals to walk with a longer stride length and a small stride height. Why is this important? I mean, it's all important in the context of people with stroke. Somebody who has stroke, they can't sort of take a long enough step, right? They're not able to clear the foot off the ground, and so often they would stumble and fall down, right? And our goal is to sort of see if we can actually have that impaired brain learn how to walk. So what we did here, and it's a simple idea, right? The person is wearing a robotic exoskeleton. He's on a treadmill, And what the robot really does is looks at the foot, right? And trains the foot to walk in a certain pattern, right? And so a pattern basically means that there's a trajectory, there's an error, and we are applying forces on the foot, right, based on the error, right? And of course, we don't do that in a single session. We have to do repetitions, right? And through practice. And I'll show you here the video one more time. This is the video of the person walking before training, and this is the person walking after training, after 45 minutes of this exercise, right? And in both cases, the robot is not doing anything, right? Because all the training was done while the robot was applying a force field on the individuals, right? And so there are lots of very interesting questions. How do humans learn, right? How do they retain? Because after all, when we're looking at human movements, we want that to sort of become a part of the life, right? I mean, when you're cycling, right, nobody has to kind of train you to cycle. And so we have done a number of studies like these with stroke patients, and there are published studies to show that these kinds of training methods actually kind of work. And people, I mean, we have groups of individuals who have had stroke, and kind of they go through this training with our in our laboratory, and you can show that they would retain some of this 6 months later on as better than a conventional group of training. So, so what we want to do is use these same neuroscience principles, okay, to show if we can improve, so we can improve athletic performance, right? And the thing that you want to sort of think about is that a small percentage difference, right? A small percentage increase in your performance can actually be sort of a big change, right? I mean, you may be you may qualify into a round, right? You may get a bronze medal, you can get a gold medal, and so forth. So what I'm showing you here is a video from one of our experiments, right? And in this case, the person is standing on a force plate, right? And there is cameras that sort of look at the various markers on the human body. There are belts attached to the human body which can apply forces in real time, okay, in response to the movement. And what we are doing here is we are looking at the capability of the person, right, to move forward, backward, sideways. We kind of create a template from there. And we want to see if I can increase their ability to sort of go beyond the template or be able to sort of follow these paths. And this is a training with one of our subjects here. And what the robot really does is kind of creates this force field, just like I talked to you about with the robot exoskeleton. As the person is moving along the path, there is a force that sort of provides that experience to them. I want to sort of show you some of those pictures here on the right. Okay, that's let's say there's a number out there, say 22.82. This is something that was before the training, how much error that you generated before the training. And after the training, it's about 11 points. Or the point that we are kind of making here is, can we use the same neuroscience principles to improve performance of athletes using robotics? And that's one of our projects that we funded by Dream Sports. And one of our roadmaps is to sort of have an intensive discussion with the coaches, players, sort of needs around the country, and see what is most appropriate for these kinds of robotic devices. So I see the vision in the future. We can design new human-robot interfaces and platforms for training of athletes. And also some of these technologies are really dual use, right? I mean, you can use it for fitness, exercise, health, and for our everyday life. So thank you.
Incredibly fascinating talk. Unfortunately, we don't have the time for questions, so let's, in the interest of moving through everybody, I'd like to welcome Juan Manuel, who is a PhD student in the Earth and Ecology engineer. Yes.
Hi everyone, thank you for the opportunity to be able to talk. My background is slightly different. Mine is my research is primarily on the theory of chaos, so I'm trying to kind of like apply that to sports, which I find it interesting. There's a famous saying in our field, you know, probably you've heard of it, like the flap of butterfly wings can cause tornadoes somewhere in Florida. So it's something interesting, and I think it's very relevant for sports as well, because as long the core concepts of theory of chaos is that you have a dynamical system, so time series, and then you have nonlinear systems, which is actually prevalent. You have interacting agents, and you have nonlinearities, and therefore it creates chaos. So chaos is everywhere. You have it in your morning coffee, swirling of the smokes. You have it in a general like Earth system circulations in Mars, etc. And I kind of like take this example from chess. Hopefully this counts as sports. There are a lot more number of possible states in chess from compared to the number of atoms in the universe, which is fascinating. Because there's so some reason like a very simple quote unquote kind of like systems where you have all the rules known but the divergence can be very massive given different initial conditions. So the challenge is that can we predict chaos, which in this case can be sports as well. So this is kind of like the normal high-level overview of what science is trying to do. So normally you have observation, you have data, can be like simulations from chess games, multiple games, historical data, and you want to be able to distill that information to come up with a reasonable model. So the idea is that can we use data to calibrate model? And this is used in many different fields in sports as well, like this idea called data assimilation, where it's used for spacecraft landing because you can really communicate with the spacecraft, and you have to like the spacecraft have to make a real-time updates given like where it should land on the moon, and you need to calibrate your weather models as well to give you up-to-date information. And it can be for financial model. It can in chess. Going back to the references that the Stockfish engine, kind of like keeps updating itself given like the current realization of what is happening on the board. So the second idea is that can we also use data to discover models? Why it's beneficial? Because data is high dimensional. Can we extract it to equations that we can like kind of like interpret and have causal relationships from this data? And this will be interpretable model. And I'm trying to kind of like discover this, the idea of like discovering systems using reinforcement learning, where, this is kind of like proof of concept where you have the reward, which is the prediction accuracy, so the time series accuracy, and the agents can be thought of as a low dimensional factor, for instance, and the actions can be like, whether you want to expand the equations or exploit, whether you want to like make the equations more complex. And the states can be the dynamical equations, which in this case can be many things. It can be like, if you want to model like how trajectory of like any time series, including like sports and things like this. So yeah, I think that's it for on my side. Happy to take questions.
Much appreciated for giving us some time back. We now have to have some time for questions. So anyone have one? If not, we can move on to the next speaker, which is Parth Gami, who is a PhD student in the biomedical engineering department.
Good. Hi, everyone. My name is Parth Gami. I'm a fourth-year PhD student in biomedical engineering, and I'm working in the ultrasound and elasticity imaging laboratory ran by Dr. Elisa Konofagu. Dr. Konofagu is really interested and very thankful for this partnership with Dream Sports. She wished she could have been here, but she's actually giving another talk in Canada, so I'll be filling in today. My project really focuses on vascular imaging for disease detection. However, what we're working on could be really revolutionary for athletes. So today we're going to be talking about monitoring cardiovascular health in athletes during exercise with ultrasound. And just to give a little bit of a background on ultrasound, I think a lot of us know about ultrasound in terms of pregnancy applications. However, it's used in a lot of different non-invasive methods to really image and understand the body. So today we'll be focusing on that vascular side. All right, so I want to give a little bit of background, the physiology of what we're really focused on, and it's the concept of arterial stiffness, why that's important for disease cases, and why that could be actually revolutionary for athletes. So every time your heart contracts, it's resulting in this pulse wave propagation that can be thought of a pressure, flow, or wall distension waveform that travels from the heart all across the arteries. So we've all done this where, we take our heart rate after running by feeling at the wrist. And feeling what our heart rate is by measuring the radial artery. So what you're actually feeling is the pulse wave traveling through the radial artery, which is causing this expansion and contraction of the artery. This is actually really useful for us because we can track this, and we can use this to then predict what the material properties of the artery is. For central arteries, which are the arteries around the heart, such as the carotids in the neck and the aorta, we want them to be elastic, meaning they expand and recoil greatly as a result of the pulse wave. As we get more, as we age and we develop disease cases, they become stiffer, which starts a loop of causing more diseases. So it's a major risk factor for cardiovascular complications like hypertension, diabetes, Alzheimer's disease, and dementia. So arterial stiffness is really profound in a wide variety of disease cases. An interesting thing, however, which we all know, is exercise can induce vascular changes. It can improve your overall health. And what people have been showing is that long-term exercise can actually aid in the reduction of this arterial stiffness. There's also a lot of work on athletes specifically and how they have better carotid elasticity and lower stiffnesses than reference cohorts. So knowing that we can track arterial stiffness in disease cases, it made us think about the opportunity, can we track this change in athletes? And can we use this to monitor training progression, optimize safety and performance, and really also screen for undetected cardiovascular abnormalities? This gives us to our topic, or that project that I'm working on, which is called pulse wave imaging. So what we're doing is we're quantifying that pulse wave as well as the blood flow that goes along with that to predict biomarkers that can be used to help us predict cardiovascular diseases, or now hopefully help us understand athletes better. So in a single acquisition of a non-invasive ultrasound imaging method, which you take the ultrasound probe, you put it on the carotid, and you scan for 2 seconds, and that's it. It's pretty simple. We can actually track the pulse wave propagation of the arterial wall. So what you're seeing here is that artery expanding and contracting. And using motion estimation algorithms, we can predict clinically relevant metrics like pulse wave velocity, arterial compliance, and pulse pressure, which is a huge thing for clinicians. Recently, we also showed, we can also do blood flow as well. And so we can actually categorize the pulse wave motion for the arterial walls and the blood fluid dynamics. This has created us in a single scan a variety of biomarkers that we can analyze per disease types or in athletes. So what we're hoping to do with our project is, if we're going to use this in athletes, we got to make sure that we can pick up the differences within individuals. So we're going to start out by doing a preliminary study on quantifying cardiovascular health before and immediately after exercise in central arteries, or like the carotids. We're going to get healthy controls in athletes and scan them before and after an exercise test, such as a VO2 test. Really, we're going to be seeing, can PWI differentiate between healthy controls and athletes? And if so, could this be used in longitudinal modeling, where maybe we scan an athlete at the start of the offseason and we see what they are at the end after training has been completed? Finally, the recent advancements in ultrasound is actually moving towards wearable ultrasound mechanisms. So instead of having a massive probe and system, these things are getting miniaturized so that you could wear it on the carotid artery or wear it in a watch format. And I've been working on this over the last couple of years of actually translating our PWI technique into wearable ultrasound platforms, and that work will be coming out end of this year or beginning of next year, where we showed we can do this in these platforms. This is huge for athletics because now if we can monitor ultrasound metrics during exercise, as well as, the immediate recovery, not at discrete time points, we could really learn a lot about this. And so in order for us to do this, we think a watch format would be the best, especially for athletes. Wearing something on the neck might not be the best. And so we want to develop a peripheral PWI method of creating an ultrasound technique with clinical standard transducers of measuring the radial artery and making sure we can get accurate information there. So we're really excited about this project and utilizing the knowledge from Dream Sports, and we think that ultrasound can really make an impact in athletes. But thank you for your time.
Awesome. We also, again, have a little bit of time for questions. So, anyone?
Same question. We get this slide.
So right now, no worries. Yeah, right now, there's actually some groups that are focused on more of getting this in real time. We right now are a very, very fast and high rate imaging technique. So we do process offline. One of our works, and our team is working on this in the back, is actually how do we reduce the amount of data necessary to predict the same metrics? So we're hoping to do that in the future, but I think that is where the field will go.
Yeah.
Not yet, but in the future.
All right. Last, but certainly not least, is Professor Vineet Goyal, who is from the Industrial Engineering and Operations Department here at Columbia.
Sorry? One moment while we locate the slide deck.
It's not a conference if there aren't technical difficulties.
Can be done.
Hello, everyone. My name is Vineet Goyal. I'm a faculty in the Industrial Engineering and Operations Research Department. And this project is joint with my colleague Henry Lam, also from IUR. And like to thank the Columbia Dream Sports AI Innovation Center for funding this work and also organizing this wonderful event. So this project is about the holy grail of so many things. Understanding user behavior. Any customer-facing company needs that as a primitive, and that is the primitive to every prescription that will follow. So this project is not shooting for, shoot for the stars in the long term, but I'll focus on more concrete goals in understanding user behavior in the context of Dream Sports. And then use that in a way that is interpretable, robust, and can be used for prescriptive problems and decisions. So the conventional approach to understand user behavior largely can be thought of as you define a utility of a user from whatever experience the platform is giving, and the behavior just a rational customer just maximizes the mean utility or some form of utility. And any user who is deviating from that, we call not all users are rational. I have a different take. Perhaps we didn't define the utility function correctly. And there's some backstory to this. How this proposal came about. At the time we got the call from the center, I was reading this very interesting book, Power of Moments by Chip Heath and Dan Heath. That the premise of the book is that there are small moments have outsized impact on user experience, and it was using the example of the Disney experience paradox. So throughout the day in Disney, customers are actually miserable standing in queues on a hot sunny day. But so if you take the average rating of their experience throughout the day, come out to be 5, 6, but it comes out to be 8 or 9. So there are those moments that the Disney theme park was able to create to get their experience high enough. And this hypothesis rung a bell with conversations we were having with Dream Sports team, where Nilesh and team, they said, oh yeah, we see users where they are continuously losing, but still are playing the same contest. and it seems irrational. But yes, there is this. There was a winning moment in the past for them or their friend that may create this behavior. So one of the important aspects of questions that we want to address in this proposal is actually tease out from data this behavior that is the peak experience, creating a peak, and then you see a decay in the engagement over time. There are a number of other behavioral aspects. I've listed only a few here, and we will discover more as we get our hands dirty with data. Some of them being network effects that are, so some users join when some other users are joining, or not join contests when some other users are actually joining. So the cognitive burden of the user not transitioning to a contest that actually might be better for them, because it's a cognitive burden for them to evaluate new contest types. So there are a number of behavioral aspects of user actions that we want to get at estimate in this project in a way that is and build a model. So one approach could be we throw a black box neural net, but that would not give us explainable insights. So the goal would be to build a model which is explainable, which is tractable, explainable, and can be tractably used in the decision problems. And the decision problems we want to focus on is, I mean, there are a number of problems that in fact, every problem, user behavior is the primitive, but two specific problems that we want to focus on in this project is recommendations and incentives. So both are very interrelated in order to maximize either the long-term engagement or long-term value that the platform can derive from the user. And a key technical challenge that we have, and that is also not special to this, it occurs in many other estimation problems, is the confounding and latent factors in the time series data that we observe. All we will see is user actions in the past and their winning and losing trajectories. Also other users joining, other users that they played with, but this is confounded with many other unobservable and latent factors that we don't see. The policy of the platform, which in the past is heuristic and perhaps unknown for the time series data. So that is the technical challenge that we will need to address in this work. So with that, I will end there. And yes.
All right, it looks like we're in question or two queued up. I think we probably have time for both, so. Just one quick question. When you talk about user modeling, you're talking about rational and logical user behavior modeling.
So yes, so can I use this? Yeah. So my sense is no user is irrational. It's the utility function that you coded was did not capture the user.
Another question: the prescriptive analytics for the benefit of who?
Okay. So it could be engagement, revenue. I think engagement is one key metric that is where that primitive peak and decay would come in.
Sounds like a really cool project. I was just wondering about if you thought about the applications of it to other user groups, and specifically in sports. You have a massive high when you win, especially if you're a player. Of course, if you're a fan, but also if you're a player, how does that affect like a team's performance over like future games? And something that we talk about a lot, you know, like the sort of emotional state of a team or a player. I know, like I don't follow cricket as closely as a lot of you, I'm sure, but like you're always talking about, you know, emotional things happening in a player's life, how that affects their performance on the pitch. We're always saying that Anushka Sharma was somehow responsible for Kobe's performance the next day. Have you thought about kind of using this model in that context? And then also, players have to be a lot more resilient, I would say, than a fan. Their entire careers on the line. Do you think that players would be responding differently to how like the average person might to like a high or low?
So, yeah, I think excellent question. In terms of fan engagement, this would be, I mean, this model abstracted out would capture, if you can capture fan engagement through some time series data, that the model should be able to tease out that effect if it exists, and anecdotally it does. And to the question of players, I think, I mean, that again is those are professional players. You're expected to not have that peak and decay. But again, I think when engagement and player performance are two different things. So maybe there are some other trade-offs which might be first order than high and low. So I've not thought, we haven't thought about the player performance aspect of it, but it should be applicable to other not just sports engagement, but other wherever you engagement with any service. This kind of models should be applicable.
All right, in the interest of time and moving on to our next event, which is another wonderful panel. Please give a round of applause to all of you. Also, one last note of shameless self-promotion. As you've seen, we have a bunch of great research awards that we've done, that we've, showcased today. There will be a call for proposals opening up back in January. So if you have ideas, please sort of reach out then, or just pull aside one of us, talk. We're always interested in, chatting about ideas and thoughts and, all that good stuff.